Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to our discussion on the principles and chemical applications of thermodynamics, and we will continue our discussion of application of chemical potentials in equilibrium of simple mixtures. And we have already seen how to use the fundamental equation of chemical thermodynamics to find out the chemical potential of the ith component in a mixture of capital M ideal gases, whereby it's possible for me to write down the chemical potential of the ith component in terms of its composition in the mixture, and this term enters in addition to the chemical potential of the ith component in its pure phase under the same condition of temperature and pressure. And we have also seen how to use the Gibbs to Hem relations to eliminate the chemical potential so that we get thermodynamic quantities like the Gibbs free energy of mixing, or the enthalpy of mixing, or the entropy of mixing, entirely in terms of the composition of the mixture, which is given in terms of the mole fraction of each component in the mixture. Now, in today's lecture, I will continue our discussion whereby we are talking about a mixture of liquids. And the situation that we have is I have a liquid phase in equilibrium with its vapor phase, and I use A as the solvent and B as the solute, and both of them can exist in the liquid phase as well as in the vapor phase. And I also assume that the vapor A behaves ideally. Under such condition, we have already shown that the chemical potential of the solvent A in the gas phase, shown in blue, that will be given by mu A star plus RT ln PA plus by PA star, where PA star is the vapor pressure of the pure liquid under the same condition of temperature. Now, this expression is valid for any liquid A which is in contact with its vapor phase while having the solute B in both the phases. Now, if I have an ideal solution, then I expect that the solvent will also obey the Raoult's law, and therefore I can replace this expression PA by PA star by the corresponding mole fraction of the solvent in the solution, and therefore I would say that the chemical potential of A in the vapor phase would be given by chemical potential of A in its pure phase, that is the vapor pressure when you are thinking about the vapor pressure of the pure liquid A. In that case, you are going to have an additional term RT ln XA. Now, this expression is taken to be the defining relationship for the chemical potential of the component A in an ideal solution. Now, we have also talked about the behavior of the solute. So, following the same argument, we can say that mu B is mu B star plus RT ln PB by PB star. But Henry's law tells us that here PB, that is the partial pressure of the vapor of the component B in the vapor phase above the solution here, this is not proportional to PB star. Or in other words, it was found that PB is proportional to XB, no doubt, but this proportionality constant unlike the Raoult's law, is something else. And this is known as the Henry's law constant. And therefore, what one does is one writes down mu b as mu b naught with a special sign plus RT ln xp. So if I use the Henry's law, then what is mu b naught? Mu b naught is now mu b star plus RT ln kb by pb star. Now this relationship is taken to be the definition of an ideal dilute solution. So an ideal dilute solution is a liquid mixture for which the solute obeys the Henry's law and the solvent obeys Raoult's law. So you have already seen that with this description in the background, we can have a generic description of the Gibbs free energy of mixing for the two liquids and the entropy of mixing of the two liquids. And interestingly, simply because we have similar type of expression for the chemical potential, which is this, then I have preserved the analytical expression for delta G mixing and delta S mixing. And you must realize that this generic expression gives us a lot of simplicity, because this is valid irrespective of whether I have an ideal gas mixture or an ideal solution in the where the two components are in the liquid phase and there is a vapor in contact with this liquid phase. Now we have going to show the importance of these kind of ideas in explaining why the solutions like the ones that we are describing here would exhibit what is known as the colligative properties. And the basis of this these colligative properties is that the chemical potential of the solvent in solution decreases compared to its value in the pure phase. And then we could show that yes, because of the presence of the solute in the solution, there can be a depression of freezing point and there can be an elevation of the boiling point. So in today's lecture, let us have a look at the quantification of how much would be the change in the boiling point of the solvent from its value in its pure phase. So the first situation that we have in mind is where the boiling point is Tb. So under this condition, you have the situation where the pure liquid A is in contact with its vapor phase, and the partial pressure of the vapor phase here is given the notation as Pa star. Now in the presence of a solute, which is shown here, the boiling point goes to Tb prime. And as a result of this, experimentally, you can measure the partial pressure of A in the vapor phase, and that turns out to be Pa. And I understand that in the solution, if I have the mole fraction of A as Xa, I can write down mu A star G is equal to mu A star liquid plus RT ln Xa. Now I am going to rewrite this equation in a way that I write down ln Xa, that must be this quantity. By rearranging this equation, ln Xa turns out to be mu A star in the gas phase minus mu A star in the liquid phase divided by RT. If that is so, now do I understand what this numerator corresponds to? As you see, in both the quantities that I am writing down, it is corresponding to the chemical potential of the liquid phase and the gas phase of A when it is present as a pure substance. And therefore, I can very easily replace this difference as the change in Gibbs free energy during vaporization when the liquid and the gas phase coexist in equilibrium as shown in this case. So now that I have ln xa given in terms of delta G vaporization by RT, I can carry out this differentiation. Now please remember, here I am carrying out this entire experiment without having any change in the pressure in which I have placed my system. Therefore, I can take an absolute derivative with respect to ln xa, and then this turns out to be 1 by r, then ddt of whatever is remaining from this expression. But it does tell us that this can be simplified further, because by the use of the Gibbs-Helmholtz equation, I can replace this derivative by minus delta H vaporization, which is nothing but the enthalpy of vaporization when the pure solvent A has its liquid and the vapor phase coexisting in equilibrium, and delta H vaporization is the change in enthalpy during the vaporization process. Now, this differential form of this equation can be made more useful, and we can integrate it. So I'm going to integrate this from the initial boiling point Tb to the new boiling point Tb prime, such that I have the corresponding dln xa going from 0 to ln xa. Because why is this 0? That is because in the pure phase, xa is equal to 1, there is no solute. As a result, ln xa would be equal to 0. So when I carry out this integration, then this is the expression that I get, that is ln xa, that depends on negative of this ratio into 1 by Tb prime minus 1 by Tb. Now let us see how we can use this further and simplify it a little more. We know that because I have a binary solution, there are only two components present in my solution. One is A, the other one is B. Therefore, by definition, the individual mole fractions must add up to 1. Therefore, I must be having xa plus xb equal to 1. And therefore, what I can do is, I can write down xa as 1 minus xb. I'm going to use this expression and replace it here. And when I do this, what I write down is ln of 1 minus xb, that is equal to whatever appeared in the on the right hand side. Now what happens if I have a dilute solution? In a dilute solution, the solvent is present in an excess, and the number of moles of the solute is very, very small compared to the number of moles of the solvent. As a result, I can say that xb, that is the mole fraction of the solute, is going to be much, much less than 1. So the consequence of this is, I can now replace this expression of logarithm of 1 minus xb by approximately by minus xb. Now if I do that, so if I replace this expression into this equation, what do I get? I get minus of xb, that is equal to whatever I was writing down on the right hand side. But what I have done is, I have now carried out this a little more simplification of this, whatever appears within the bracket, and this turns out to be something simpler. Now what is it that I have put in here? I have taken off the two negative signs from both sides of this equation. Also, I have noticed that this delta Tb prime minus Tb, this is the delta T, that is the magnitude of elevation of boiling point because of the presence of the solute. And I also note that in the absolute scale, if I have a dilute solution, then only a very small amount of shift in the boiling point will occur, and therefore for all practical purposes in the denominator I can replace Tb prime by Tb, so that now Xb is shown to be proportional to delta T by Tb square. So here I understand that by dissolving Xb mole fraction of the solute in the solvent, I would observe an elevation in the boiling point whose magnitude is going to be delta T, and delta T is going to be proportional to the mole fraction of the solute. And the proportionality constant now I can find out exactly, which is given by RTB square divided by delta vaporization H. Now this Kb prime is called the empirical boiling point constant of the solvent. Actually, for practical applications, this equation is extremely useful, but it might require you to modify a little, because here I would like to know explicitly the role of the solute in giving me a certain value of delta T. So if I now examine the role of the solute, delta T depends only on Xb. That is the only place where the contribution of the solute is coming. Now what is Xb? That is the mole fraction of the solute. Now does delta T depend on the identity of the solute? The answer is no. And therefore I can say that this elevation of boiling point, as given by the experiment that I am looking at, this must be a colligative property by definition. Not only that, for dilute solutions, I can write down Xb by definition is this. Now if I have a dilute solution, then Nb is much less than Na, and therefore in the denominator I can neglect Nb and I can replace Xb approximately by Nb by Na. Now what is the consequence of using this expression? You understand that while you prepare the solution, you will be dissolving certain moles of the solute in, say, a few kgs of the solvent. And then instead of mole fraction, you would prefer to use the molality of the solute, which has the unit of moles of solute per kg of the solvent in this particular expression. Now, what I understand is, in this case, B is defined as Nb divided by Na into capital M, where capital M is the molecular weight of the solvent in kg. Therefore, what is Na into capital M? That is the weight of the solvent in kg if Na moles of the solvent is present in the solution. And therefore, if Nb moles of the solute has been dissolved in Na into M kgs of the solvent, what is the molality? The molality is going to be given by Nb divided by Na into M. But we already know that for a dilute solution, Xb is equal to Nb by Na. And therefore, I understand that if I am adopting B as the scale for the concentration of the solute, then this B is related to the mole fraction as xp by m. Now look back at the original expression that we have derived. Delta T is equal to Kb prime into xb. Now I'm going to modify it a little bit. I'm going to write down what Kb prime is, and then I'm going to multiply it with the molecular weight of the solvent in kg, and therefore here I have to divide it by the molecular weight of the solvent in kg. And if I rewrite this expression, what I get is delta T, that is equal to Kb, which is nothing but Kb prime multiplied by this molecular weight of the solvent. And now instead of mole fraction, I have the concentration of the solute expressed in terms of molality of the solute. So here I understand that for practical applications, if I want to know the delta T, that is the amount of elevation of boiling point, then delta T will be given by Kb into B, where B is the molality of the solute, that is the number of moles of the solute dissolved per kg of the solvent, and Kb, that is the empirical boiling constant of the solvent, would be given in the units of Kelvin, kg per mole. Now, what I understand from all these lectures is that we have been able to justify the role of the solute. Now, let us have a critical look at the role of the solvent in the elevation of boiling point when a solute has been dissolved in the solvent. You would remember that we have discussed the Troughton's rule in an earlier lecture, and the rule states that for most liquids, the standard entropy of vaporization is a constant. And in general, experimentally, it is found that the standard entropy of vaporization for most liquids is given by 85.0 joules Kelvin inverse mole inverse. Now, since I'm talking about vaporization, therefore I can rewrite delta S vaporization under standard conditions in terms of the enthalpy of vaporization under standard condition and its boiling point. Therefore, I understand that this quantity must be a constant for most of the liquids. Now, if I am thinking about this experiment at a standard pressure of 1.0 bar, then I understand that I can rewrite the empirical boiling constant now in a way that would include the standard entropy of vaporization. And then I understand that delta T under such condition would be proportional to Tb. So what does it mean? What is the implication of this apparently very simple expression for the elevation of boiling point? It means that the largest changes in the boiling point occur for solvents with high boiling point. So basically, if you are using the same molality of the solute, in that case, you find that delta T for different solvents will depend on Kb. So if you want a larger increase in the boiling point, for the same molality of the solute, you must have a larger value of Kb. Now look at what Kb is. Kb depends on Tb as well as this quantity. And the standard entropy of vaporization is a constant across a wide range of liquids. Therefore, Kb would be higher if Tb is higher. Now, what is Tb? That is the boiling point of the solvent. Therefore, I will have a larger value of delta T if the boiling point of the solvent is higher. Now, here are some of the typical values of the empirical boiling point constants for a wide variety of solvents. Now, please note that instead of Xb, you can actually write down the molality B to express the delta T. Now, as you see, amongst the solvents listed over here, who is having the largest value of the empirical boiling constant? The largest empirical boiling constant is given by phenol. And who's having the largest empirical constant here? That is smallest one, that is water, and benzene is intermediate. Now that we have learned something about the elevation of the boiling point, I can now have the same line of argument and consider the depression of freezing point as well. But here the experiment that you will be talking about is where you have the solid solvent A in equilibrium with a liquid in which you have dissolved a small amount of the solute B. So at equilibrium, I must be having mu A star solid, that is equal to mu A star liquid plus RT ln XA. So following the similar argument as we have shown in the case of elevation of boiling point, now ln XA would be given in terms of this quantity, where the numerator can now be replaced by the Gibbs free energy of fusion for the pure substance A. And then if I take the derivative with respect to temperature and do an integration, what is it that I get? I get that ln XA that must be related to this ratio, and Tf prime is the new freezing point of the solution that is in contact with the solid A. And once again, I will replace XA by the mole fraction of the solute, and I would be able to say for a dilute solution XB, I can carry out a little bit of simplification, and then by denoting delta T as del Tf minus Tf prime, I can very easily show that delta T is equal to Kf prime into Xb, where Kf prime is known as the empirical freezing point constant of the solvent. And as you see that here it depends on delta H fusion for the pure solvent A. And once again, I understand that the delta T, that is a depression of freezing point that I see here, that depends only on the mole fraction of the solute. It doesn't depend on its identity, and therefore once again, by definition, depression of the freezing point is a colligative property. And for practical applications, if I change the way the concentration of the solute enters the expression, then I can show that delta T is proportional to the molality of the solute, and the corresponding freezing point constant turns out to be RTF square into molecular weight of the solvent divided by the enthalpy of fusion of the pure solvent. And here is a list of Kf values for different solvents, and as you see that in this case camphor provides the largest value of Kf. Therefore, if you would like to have the largest value of depression of the freezing point for a given molality of the solute, this is the solvent that you will choose. So in conclusion, this is what I would like to highlight here. we have looked at the way to describe liquid mixtures. We have seen that by preserving the format of the chemical potential as something plus RT ln into the concentration, we can arrive at very generic expressions for the free energy of mixing, irrespective of whether I'm dealing with a mixture of ideal gases or an ideal solution of B as a solute in A. We have already also talked about how to justify, using the same kind of expression, the existence of qualitative properties as exhibited by the elevation of boiling point and the depression of freezing points. There are other qualitative properties like osmotic pressure, which I have not discussed in this lecture, but if you are interested, you can look it up in your textbook. So at this point now, we are ready to take up more complicated situations whereby my system is comprised of more than one components. These components may be a mixture of ideal gases. They may be a mixture of non-reacting ideal gases, or they can be a mixture of reacting ideal gases. I will consider the thermodynamics of a mixture of reacting ideal gases when I talk about the chemical equilibrium in the gas phase. We have also seen that when I have these solute and the solvent, and if they are non-polar, in that case we can handle the mixing of these liquids in a very simple fashion, very similar to the case of ideal gases. But what happens when I have a liquid mixture where I have different phases of the components coexisting with each other? Additional complications might arise if there are charges on the solute and the solvent. So these are the kind of situations that you come across when you talk about electrochemical systems, where you have a solid electrolyte, a solid electrode in combination with a liquid or a solid or a molten electrolyte, and you have a chemical reaction going on, and you would like to understand the equilibrium in this very complicated electrochemical system. Thank you.